We have a very short slideshow and this kind of stuff. Then we go back for the actual projects. I think everyone knows what is PCB is. So, okay. You in the lab, you connect different parts together, like transistors, LEDs, resistors, and these things. You connect them using those breadboard, you solder them, or you use hard wire to connect different parts of your circuit together. Okay. But of course, this is not applicable, and you want to sell it on the market. You want to make it permanent. It's not possible. So you need to find a permanent solution. Solution is the PCB. We built something that can hold all of this connection, that connect all of the things together, and it is permanent. It is not like the things you bring with yourself. You lose some of the wires, you don't know how it works, and this. So for your final project, you need to design such a thing. But our lecture is about how to design, how to implement, how to build one of them, and how it works. Okay. This is just a layout of a PCB that, and the elements of it. So you see those wires are called tracks, and these are called pads. Pads are the thing that your components go through. Go through it, then you solder it, and they are connected. These points are connected together as you connect on the actual breadboard, and then they are connected and just turn it on and fine. Okay. But PCBs can be more complicated than this. Some copper piece and one sheet. It can be more complicated. The good thing is on those, when you connect the wires together, it's sometimes hard, but sometimes you have more flexibility. You can connect everywhere to everywhere. But on PCB, we are working on a 2D. Plate. But if you want more, you need to go more than 2 layers. So this is one of the schemes you can use. There are more than 1 layer on each other, one on the top, one on the bottom, and can be many of them in the middle. The thing we can build in this university is only double layered. One on the top, one on the bottom.
What is the advantage of multiple layers?
Gives you more flexibility to connect different things together. You are working on a 2D area. You cannot pass some of the signals. You don't want to short circuit them. So you need another pass. Another pass is not possible on the same surface. You need to go to another layer. You go up from underneath. And I'll show you on the software how we designed it and how it works. And we will build one on the lab today, and you see how it works. But multiple layer, more than 2 is not possible for us. We don't have enough equipment for that. Most of them are built by industrial prototyping. There are some prototyping devices that do that for you, but they are very expensive and it's not, economic or feasible for universities to buy. So mostly the companies use them. But there are some prototyping devices that do those things. Okay. These are called through-hole components that goes through your PCB. From one side goes to the other side. You see they have pins. They can go through your PCB. So you do these holes. Your PCB needs some holes that these guys pass through. You know all of them. There are not capacitors. A transistor is a metal transistor, and this is a resistor. Of course, you know them. But there are some of the components, they don't go through your PCB. They are mounted on your PCB. They are called SMD, or surface mount devices. They have almost all of the things, capacitors. These two are capacitors. ICs, that's all of the ICs you have seen. Even LEDs, resistors, all of them. So it can be like that. But this is the thing. This is why we need to use some kind of technology, some kind of fine technology to do these things, because today everything should be smaller and smaller and smaller and smaller, and should go to your phone, should go to your pocket, and lots of complicated circuit. So you need some technology to do that. You cannot do this with older stuff like I showed you some of them. So we need to make them very fine, very small, and sometimes it's not possible for us to work on them, like for example, mount them or assemble them. It's not possible. It should be done by machines. Most of your devices are done by machines, and it's not possible to do it by hand. It takes ages to do that. Okay, so this is a small LED on tip of this guy's finger, and even there are some smaller parts that even you cannot visually see that they look like dust. Okay, this is a finished product, but this is a finished product that has through-hole components on it, assembly component and assembly chip, assembly capacitors. You see C6 means capacitor, and if I see some resistor, and this W1 and 2 are through-hole things, which goes through your PCB, and these kind of connectors, they all go to the thing. And this guy has 2 layers. If you look at it, you see some of the tracks running through the upper surface, and of course there are some of them behind the scene. You don't see them, but I show you on the software and how it works. And you see, you can have lots of beautiful things. You can have printing on it, seal print on it. But we don't do these things. We just build the body of the thing. The other things, they are more complicated, and it needs more equipment. So it's not done by companies. You send them a plan, a plot. They send you back such a thing. Okay, how to build them? I want to mention about them. There are lots of ways, but I want to mention. Photo etching is I can say one of the oldest ways to do PCBs. It uses a very simple logical thing that you need to do with such things. They are called films. If you want to look at them, they are called films. They are called films. The PCB is a surface, a board, and the whole surface is copper plated. All of it is copper plated. There is nothing but copper. But what we do, we remove the parts we don't want, we keep the parts we want. They laminate it with some photosensitive thing, then they put these things on it, then they project some light on it, mostly UV. Then with some solvents, they solve the parts they are not exposed to light. Then they put the whole thing in the acid. The places they have no protection, they will solve in the acidic solution and take. And the other parts which you see on the films will remain. This is how it works. This is called protection.
But how like there are wires, they will burn wires on the board or something? Or
There is nothing like burning, just the whole thing is copper.
okay.
We just remove the parts we don't want by solving them in the acid. And we keep the places we want. The whole tracks you see on those films will be protected by some photolaminated thing, photolaminated material. So they are protected. The other parts which have no protection will be solved. And I show you the real material in the lab that you see the whole surface is covered. And the second one is milling or CAD-CAM. I Actually, CAD is always there, computer-aided design. Even if you want to do the photo etching, you do the CAD. You just draw your PCB with some software. Then you just print it on these films and do the photo etching. But CAD is computer-aided machining. We do some machining. Okay? We remove the parts we don't want by doing some mechanical action now, not mechanical. There are some tools like this, you see, they remove the things we don't want, and at the end gives you the final product. Now I want to show you some things. Let me run my software. And I can show you some products that I did. Some, the finished product is assembled one.
Which one is better, using a chemical to solve the...
Actually, this is a very good way for just prototype. In industries, when you want to do mass production, this is impossible. It is very expensive for mass production. The good one is, no, this one is even good for mass production, but not very complicated. It becomes complicated and finer, they become, tracks become thinner and thinner, components become smaller and smaller. Even this one is not suitable, so they use some laser new technologies that activates the boards, they create some copper on it, then it needs some complicated test thing, for example, X-ray test that shoot into the, when you have lots of layers, you cannot visually see what's in between. So you need X-ray to see what's going on. So this is some of the films you have in your hand is the film of those PCBs. This is the finished one. It is soldered. It's the same board you have in your hand. It is soldered. It's a multi-purpose thing. It can be rectifier. It can be motor driver. It can be inverter. Actually, it's an H bridge, but the input is digital. It uses a microcontroller. The clutch chip you see, it's a microcontroller. Okay. There are lots of software you can utilize to do these things. The first time I did, I found something called Protel. It was before 2000. After 2000, Altium Designer came to the followed the Protel, and it uses almost the same thing. I think it's a very powerful tool, but there are some others if you don't want to use Altium. It has a student version, you can buy it very cheap. And there are some others like Proteus. That one is fine. And PCB Wizard. PCB Wizard is fine, but it's not very well for CAD-CAM. You know, one of the problems I have is I have problems with holes in PCB Wizard. And of course the rules and constraints. There are some rules and constraints on in designing PCB, so I want to show you some. The thing I show you are same in all of the softwares. The terms I use, all of them are same. And I don't want to go to the wizard things, I just show you how I draw by hand. I don't want to do it because there are some wizards that do these things for you. Okay, I just build a new one, a new PCB, and okay, this one goes back. Okay. This is my workspace. Let me just start my screen record. Okay. No, this is my workspace. This is what happened to my workspace. It's gone. Where's my okay? This brings my workspace back, but there are things. This will be generated and built on a real material. So measurements should match each other. Measurements are very important. Even microns on PCBs are important. So Altium is an American software, so its default is imperial. It works with inches and mils and these things. I don't want it, so I changed it back to metric. These things are similar to all of them, but the menus and things are different, but the things I want to show you are the same. So I changed it to metric, and I changed the snappies and these things. You will find it on the other things. It's fine. Don't freak out. It's nothing important that you want to. Okay. What I have. There are something called footprint. I want to bring you a footprint that, for example, you have seen that PIC chip, yeah, it has 40 pins and these things. So this is called DIP, dual inline package, and 40 means it has 40 pins. So I bring one of them. It's a very standard thing. So the size and this is predefined in such a software. Okay, so I bring one of them on my view. Just I put it on my PCB, and you see all of them. Right. But how can I measure things? For example, I want to first I want to see what is the hole size, what is the pad size. I just double click on it. It says, for example, your hole size is 0.9 millimeter. Your X size and Y size is 1.5. Let me change this one to see what happens. Okay, 2 comes. So this one is the copper. This one is the hole. So it shows me a kind of visualization that what is this. So when we finish the product, this will be copper, and there is a hole between in middle. It is here. Okay, that's it. But I want to add some things. For example, I want to add some LEDs for you. I can come to the footprints and I find some things for you. These are not exactly same on all the software, so don't worry about this. I just put something like, for example, I want to do some LED, let's just start with resistor. But there are lots of resistors, axials of resistors. So whatever, let's put one of them on the view. Let's see what happens. Okay. This is my resistor now. Let's zoom on it. Okay. But how can I know what is the real size of it? When I build it, what happens? Size from here to here. I don't know it. It's not visible. It's more than 10 centimeters on my screen, but it really is not that. So I need to have some measurement tools. So Control M measures in this software. There are other shortcuts and things and produce and PCB result that you can measure. Okay, I can measure. It says 7.62 millimeter. But how can I measure something real on my? I have a component. I want to put it on this one. I want to see does it fit or no. So how can I measure it? I have a device here. It's a tool. It's called caliper. The thing you need to use most of the time in design PCBs. Mostly when you don't know that you use some components and you don't have footprints. There are capacitors are not same size. Resistors are not same. Different components may produce different things. There are, for example, resistors are mostly standard size, but capacitors lots of different size. Some of them are smaller, some of them bigger, but same value. This is the caliper. With this one, I can measure my distances from the pin sizes, the distance between them, all of these things. I'm sure you have seen these things in your physics lab, and you know how to work with it, but it's not bad to have one around when you want to design PCBs and make sure that all of your sizes are correct, because you build a PCB and you go home, you want to assemble the components and say, oh, does it go in? And there's no other way. You should throw it out. So this simple mistake that ruins everything. So this is how I measure this thing. I don't think it is what you see on the screen.
The distance you measured, that will be the real distance of the PCB of the component?
Yeah, that one was a real distance.
Okay, and for example, if you don't know the footprint of a component, we'll measure through this. I mean, using this circle.
I can build one. For example, I want to have a bigger resistor. I use here place pad. These are called pads. Pad goes from the top side of the PCB to the bottom side. That it's a hole. It goes from this side to the other side. It's open. So I can bring one of them. Okay. I put it here, for example. I want bigger. I put the other one here, for example. I want bigger. So then I use Control M to see what is my distance. For example, okay, that's it. It's okay. I'm satisfied with it, or I want to, for example, I change it a little. If I want to align them, all of the softwares have things to align them. By right-clicking on them, you have align. It says if you want to align them on the top of the one of them as a reference, it brings them on same Y. If you want to align them to the left, it brings them to the same X. You can align them together. You can change the distribute horizontally. You can align by centers and all of these kind of things. You can do them with these kind of tools, and they are available on Produce, on Altium Designer, and I don't know exactly what the PCB is. PCB Designer is the simplest one. I don't know. It has all of these tools. Okay, let's see. Okay, this one is, for example, it doesn't suit me. I can use some other footprints that it is available on Altium. And there are lots of footprints you can download for all of the softwares. So I go for 0.4. It's a little bigger. Okay. I measure it again, for example, from here to here. Okay, 10 millimeters suits me. It's fine, so I remove it. Okay, I remove it from here. Okay, now I want to connect it to, for example, this pin on PIC is master reset. Yeah. I want to hide this one. I don't like it, or I can use it, for example, to write something on it, for example, R. Okay. And I tell you one by one what are the colors. Colors are different, and I tell you items. Okay. Now I want to do a track, but on which layer? Top or bottom? I have here, I can check these ones. Which layer do you want to? I say, okay, go from bottom layer. I come here, I take my tracking tool, and it is available on all of them again. I do this, comes and I connect it to here. Okay, that's it. This is my tracking. But let me do something here, because I changed the settings to give me warning when my tracks are not the size I want. So I want to change my design rules. If I can find it, rules. Widths. I want minimum widths, maximum widths. I say okay. My maximum widths I want to be maximum of 2 millimeters. Because I don't want to see the green color. I want to see the actual color. Okay. No, it turns to blue. Green in this software means warning. Warning. It has lots of things that you can define, lots of rules, the clearance of them, the size of them, all of these things. For example, I go close to this one, it turns to green, means oh, you are too close now. So let me just rotate it with a space. I can rotate it, and then I put it here, for example. And if I want to go to on top layer, I just click on top layer. I just draw another one, for example. It's just an example. Okay. One of the things here is Altium and most of the others. When you want to connect one place to the other place, automatically generates a 45-degree break. But I saw, for example, on PCB Wizard, you have this problem, it doesn't generate that one. And it is a problem. Trying to not to use I can use it. If I insist, I can use it. But normally it gives me a 45-degree of breaks. That is fine. When you want to use those signals, do not use something that has 90-degree of turn one. So if you want to do a 90-degree turn, do it like this with 245 degrees of turn. Ultimate does it automatically for you. The 90-degree turn gives you reflection. In higher frequency, gives you reflection and noise at the edges. Avoid pointy things on your PCB. Try to, increase your angle to avoid from being pointy. Do not go, for example, 90 degrees or less. These things are not fine.
So why we need to avoid pointing? Why we need to avoid the thing pointing?
One of the things, let me show you something. If I do such a thing that it is 90 degree, the signal comes here in higher frequencies, it hits this one and reflects back. Some of the power reflects back through the same track. So this is not working. This one, when it hits there, goes the other way. So this is one of the problems. The other problem is, you remember in the physics and these things that charges and these things concentrate on the pointy places always. So avoid them. And pointy things are very good things for radiation. So when you have higher frequency, more than 50 kilohertz, 15 kilohertz, they start radiating. So avoid them. Avoid loops on your PCBs. A signal goes the whole thing and goes back to the same place, avoid that. And especially ground. Do not use a ground that goes through around all over PCB, comes back to the same place. If you do that, you make an antenna for signal, or for the ground you make different level of ground for your circuit. So this is not it. These are the simplest things of PCB, and you, in all of your studying this 4 years of university, if you just do these things, it's fine, nothing more. If you see some of them, you will see some planes under my PCBs and these things, they are called polygons, and these things I cover some part because there are some noisy, those circuits are some very noisy circuits. They are for SMPS and this kind of switching thing that generates lots of noises on the line. So I need to protect my things, but most of you don't need them. But sometimes, if you want, there are some shapes like these kind of polygons and these things, you can bring them on your PCBs if you want to cover some parts. And you see, when I cover it, my tracks doesn't go into the ground, those plane. It's out of it. But don't do that, because in this university we use milling things and we don't cover it. If you look at those my PCBs, all of the places I don't want to expose them to soldering, and these things are covered by something green. So I can solder them. But if you do that, the thing I did, and use it here without that cover, your soldering flows over them, and it's a big headache to remove them. So this is not okay. If you want to design and send it to some people that they are expert to do this, they have all of these equipments, it's fine, do that. But in this university, please don't do that, because it becomes a very big headache. So I just remove it. So let me show you some nice things that you may need it. The packaging that I want to say, all of them are same. They are standard names. I told you DIP 40. You have DIP 8, for example. Your op-amp is a DIP 8 thing. What is your favorite op-amp? LM741. This is LM741. It uses a DIP 8 package. DIP 8 package can be lots of things. It's only a package. There are lots of parts that go through these kind of things. Your regulator, when you want to put some thing that gives you 5 volts constant. 7805005. It's called, I prefer to find it because it has some things. It's called TO220. So the thing you see TO220, and there are some things like this. That,
How do you know the number?
there are package names. Whenever I wanted to use, I read the data sheets, and this in the data sheets it specifically says this is this package TO220. Your transistor, what is your transistor? 2 and 3, 9, 0, 4 and 6.
Yeah.
They are called TO92. Their package name is TO92. Okay. The package of that regulator is TO220, and there are lots of other packages. If you learn them, it's very fine. But most of the packages are provided in these kind of softwares. You don't need to design them again. Just as an object, you can bring it on your app and do this. Was it? Okay, TO. Okay, let me show you things. Okay, zoom in. Okay, the pin 1 is square, the others are round. Means it wants to show you which is the first one. If you see on the data sheet, it says pin 1 is the input, middle one is the ground, the right one is the output. So they are mostly provided to TO92 if as this is your beautiful transistor you work with. This is the footprint. You just bring them and put them on the. But what is the yellow one? Yellow one is called top overlay. Is the thing that these kind of white things you see that guides you when you want to mount them, you want to assemble them. So the yellow things are in top overlay. If you want to write something on your PCB, for example, this guy says PIC user interface, you want to write them here, such a thing, you bring some text, then say for example, this is a test. So you put it on your top overlay. And there is bottom overlay. If you want to use it, you can use it, but mostly we use this. But we don't create them in this university again. So we don't need it. So we leave it as it is. If you want to just when you finish the building and you want to assemble it, it helps you very much when you look at your computer. It helps you out. So let's do a very small thing to just build it in the lab and have a little fun. Okay, what do you want me to build? Any suggestions? Any suggestions?
A microcontroller project?
You want microcontroller?
Yes.
Okay, let's do a microcontroller one, then you can assemble it and have fun with it, okay? I just do it fast because I don't want to lose time. I just doing these things. Okay. I need a regulator.
Engineer,
Yes.
can you use move sensor in the micro?
Sorry?
Move sensor.
Move sensor?
Yeah.
What do you mean by move sensor?
I mean like transistor. Something like transistor.
Transducer?
I don't get what you mean.
Transducer, maybe.
I just want to build a very simple PCB that you can assemble it and just blinking LED or something like that. It shows you how it works. I don't want to go to the computer, then you can install and do your things on it. So it's better to just do these things. Okay. Let's have two nice pads here just for connecting your power supply. Okay. This is your power supply. let it be here, then I have it here. I want to go from my bottom layer, I go from here to, of course the input is this one, yes. Okay, this is my ground. I go from my ground, okay. Oh, I lost it, I keep it on again. Okay. Which pin is the positive? Which pin is negative? Do you remember? You can check it on the internet, you download it on your mobile phone.
Yeah.
I don't have my mobile phone today. Let me just bring it very close together. One of the things on these kind of things, try to compress everything as possible. Although sometimes you need to make it bigger for other kind of stuff, but these kind of microcontroller and this, compress them together.
Pin number 11 is VDD.
Okay. Have it on your thing. How can I find it here? My pin number. I just zoom in it. It says, oh, this is pin number 11. So VDD is
This pin 11.
11. Okay. I come down 11. Let's find 11. Okay. So this is my pin. I go in. That's it.
There is another pin for VDD.
Oh, it's fine. I don't want to get. What is the VSS?
VSS 12.
12. Okay. No. VSS is the ground, so I want to connect it to the ground. This is pin 12, yeah?
Yeah.
I just come from here, right away, from here to here. Okay? Is it fine? Try to avoid these kind of steps. For example, if I could connect it like this, but it's not fine. Try to just avoid some kind of steps that things like this, for example. Just avoid these things. For example, here. Try to avoid these things as possible. But if you couldn't, sometimes it's not that bad. You can use these kind of things, but avoid as possible. Okay, I just connect this here. Okay. Then I want a resistor here for your master reset. So I come here to my devices. I go for this one. Okay, I put it here. Let it be. Let's save some space. Okay. Here is fine, I think. Okay, then go together. I don't want to these design designators. They are not nice. Or you can, let me, at least this one, let's call it 16F877, yeah? Let it be. It's nice, sometimes you have this. Okay, this is my output. This is my output. Okay. This is it. Then I want to use this port for some LED. Okay. Your LED, I think, fits in. If I'm not mistaken, it should fit to such a thing. Let's see. These are LEDs. It fits on this one, but it is for these kind of LEDs that comes out of the board. So I want to make it smaller. It should fit in this one, I think. Let me measure it first to make sure. It should fit. I'm sure it fits. 2.5. But okay, even if I make it a little bigger for you, but if it's not important that exactly when I want to exactly have you see on those boards there are some LEDs that exactly on the board, you know, the pins are fit exactly on, goes through the holes. You have to measure them. Some of them I designed in my hand, so go for a little bigger one. Let it be big, nothing happens. Let it be a button like this. And we can program your chip out of the board. So I show you sockets because I don't want to add things. So let's have some. Okay, let's do this. I go through it. Nothing happens. It's fine if you want to go through them. I can use the copy and paste. It's fine. Control C, then I click on it. Control V, I bring it here. You can copy and paste. Okay. Then I come here. Then I just. Is it okay? Makes sense? There's an LED and a resistor in the path.
Yeah. There's another pin for BT and BTS on the other side.
You don't need to connect them. You don't need to connect them. They are internally connected together. Sometimes if you want to use more pins that send signals to lots of things, lots of switching things, you need more power on those pins. You connect all of them. Or sometimes just for flexibility. Sometimes you put it on the board. It's very hard to connect the things from here, so you go from the other side. So, do you need an oscillator on it? No, you don't need. It has internal oscillator, so this simple circuit will work. Right? So it's fine. But the thing is, how to build it? How to build it? This is the tough question. Let me just check all of these sides, then I show you. Okay, we draw our PCB. How can I transfer it to a PCB?
You need two holes for crystal oscillator. You need two holes for crystal.
I can use internal oscillator, nothing happens this time. It has internal oscillator, so you don't need to even put something on it. If you want to put it, okay, just if you want to use it later on, which pin they are?
Yeah, crystal 13.
13.
Sorry?
13 and 13.
These two? 13 and 15?
Yeah.
Okay, I do a trick here because your crystal is not a crystal oscillator, it's a crystal. Crystal oscillator and crystal are different. Okay? Because they don't fit on the this distance, I make it a little bigger. Just for further uses if you want to use it later. Okay? Is it okay? But what happens now? Okay, I did it. So what should I do? So now I have to generate a file that that machine can understand. My machine doesn't understand this one. This is just some things. Doesn't understand it. So I need to talk to that machine. I come to the file. I come to the fabrication. Or in the PCB result is on the tool. But here is fabrication. Then I say, okay, I need Gerber files. Gerber files are things that I can put it on that machine that to work. Okay? Okay, Gerber file, give me a Gerber file. Inches or millimeters, I say, okay, millimeters, give me metric. You can use anything, I prefer this one. It's kind of format for that file that 4 digits for the other side and 3 digits for after the decimal. So this is fine, that suits me. I come to the layers and say, okay, which layers do I want to export? I say, okay, I want the bottom layer. I want to keep out layer. Oh, I haven't designed the keep out layer, so let me just do the keep out for me first. Okay, keep out is the thing that shows where is my board edges. So I do the keep out. This keep out is okay to be 90 degrees. So I think make it 90 degrees is fine because I want to cut them from here. Okay. Okay. And this distance is okay, but let me increase it a little. Just if I increase it, because I want to cut it from there. My tool is 2 millimeter. Okay, I need to go back to bottom layer. Okay. File, fabrication outputs, Gerber files. This is okay, millimeter. This is okay. Layers. Okay, give me bottom layer. The thing I want to build.
What's that pink line for?
The pink one is the board outline. Means where is my board corners? I want to cut them from on the device, so I need to have a reference to cut.
Okay.
So I call it keep out or outline. Okay. I say okay. Give me this one and give me the keep out. Okay. Drilling, I don't want it now. I tell you why. Devices, some devices are not very compatible with that one, so I need to do another. Okay, that's it. It's generated. Thinking. Yeah, that's it. Now I have my tracks. Okay. Then I need another thing for drilling because I want to do all together. I want to drill it. I want to make pads. Okay. Again, I come here fabrication output NC drill. NC means numerical control. Numerical control. NC drill file. Give me this one. Same thing. And I don't want to change anything. Just this. That's it. Okay. I don't want to change anything again. Okay, these are my holes now. Okay, but again, this is not suitable for that one, so I need to export it as Gerber. This one as Gerber. So I say, okay, I need Gerber X, all of these things. Okay, put it on my desktop. Okay, let me just build a new folder for you, the PCB. Okay, PCB Workshop. That's it. What happened to my toolbar? Okay, desktop, PCB Workshop. Okay, it is well okay. I'm sorry, I picked the wrong one. This is the Gerber one. The tracks are Gerber. Okay, Gerber X. Okay, that's it. These two, each layer, bottom and border. Put it on my PCB Workshop. That's it. The other one, export it as. Well, I don't need to, I just save it, I don't need to export it as a specific format. Because it is NC now, so I just say drill. Layers, this is the only layer. This one, let it be metric, this one is okay, that's it. Save it as, same thing, but cam.drl now. That's it. This is the whole thing we need. Here I have some text files that does this. There are text files actually. Let me take a look at it. Work that. This is the thing. It says G92 means my location absolute. Means give me a point. So from that place I go everywhere I want. I want that. M48 means run the spindle. I showed you the spindle already. Okay, metric FMAT 2 is something like that. Forget that one. T01 means tool number 1, which diameter is 0.7 pick. Okay? It's the tool list. It defines the tools. It doesn't mean pick them. It defines the tool that I need those tools. Tool 0 is this one, tool 5 is this one. Okay? Detect, on. G90 means go back to reference. Take the T0. Go to X this, Y this. Then go to Y this. It goes here, goes down, comes back, goes to here. Means X doesn't move now. Goes to the Y direction, goes in, comes back. Then come and pick tool 2. Then go do these things, pick tool 3, go down, do all of these things. M30 means finish. That's it. This is all of my tools. And this is of course the GKO, for example, if you want to GBL, you want to see them. They are same, but are a little more complicated because it goes through the thing, goes back, does lots of things, does lots of interpolation things and these things to go through the paths and these things. This is the whole thing. That's it. This is the whole thing. These 3 files, we give it to that machine, everything is done. Okay, so guys, this part of the thing is finished. We go to the next one, we'll see you in the lab.